Okay, so this is a second order differential equations video, and we're talking today about boundary conditions. We're going to try to solve a differential equation this time, but rather than getting a general solution, we're looking to get the solution, the only solution. In order to do that, we need to work out what the unknown constants are, and that's what these boundary conditions here are. Boundary conditions you've seen before. You've seen them in things like C1, C2, where you tried to solve dy dx equals an integrated, and you had maybe what x and y was to find out what the missing c constant is. So essentially doing the same thing. We need more conditions here because we've got to find what a and b are, so we need twice the amount of information to do that. So this differential equation we saw in the last video, the fourth video, and we found out that the general solution to this particular differential equation happened to come in two parts. It was the minus 5 for e to the 2x, which is the particular integral, and then the complementary function, a e to the minus 2x plus b e to the 3x. So if you're not sure where that's come from, that's from the last video. We solved this to find the general solution. We're now looking for a specific solution given these boundary conditions. So you see we've got some information here. We know that when x is 0, y is equal to 3 over 4. We could plug that in here. That gives us one equation for a and b. But we also know that dy dx is equal to a half when x is 0. We can use that to get us another equation. In fact, let's do that. Let's differentiate this so we've got a dy dx. The first step then is to differentiate it so we can use this information just here later on. Differential here, well, bring the 2 to the front and it becomes 5 over 4 times 2, so it becomes 5 over 2, the 4 and 2 cancel down. Differential here is minus 2a e to the minus 2x. Differential here is plus 3b e to the 3x. There's two equations now. Let's use the information in both equations. So the first equation, y is 3/4 when x is 0. E to the 0 is 1, so they quite often choose x being equal to 0 for a lot of these because you get 1 and 1 gives you quite a nice little equation. If you just bring this 5/4 the other side, we get 2 is equal to a plus b. That's the first equation just there. Do the same thing for dy dx. So dy dx is a half when x is 0. So we've got again nothing to worry about with the x's, they all just appear as 1s. And if we rearrange that, bring us to the side, I think we get 3. So 3 is equal to minus 2a plus 3b. That's the second equation. And there's lots of ways of solving this now. I'm going to times this guy here by 3 to get 6. 3a plus 3b, because I think I can get rid of these two equations by subtracting to get the 3b's. So when I subtract, I prefer to change the signs and add because it makes it easy in my head. So if I add these together now, that gives me a 0 there, gives me a 5a, and that gives me a 3. But really what I'm doing is solving two differential equations, so you should have plenty of methods to do that, substitution or however you prefer. There's no mysterious things going on here. That's my first solution. Plug it in up here. I've got that 2 is equal to 3 over 5 plus b, and so b must be 2 take 3/5, which I believe is 7/5. Given that information, we can go back to our original solution. Y is equal to minus 5 over 4 e to the 2x. A is equal to plus 3 over 5 e to the minus 2x, and b is plus 7 over 5 e to the 3x. And that is your specific solution using your boundary conditions. So it really isn't that bad, is it? It's very reminiscent of that sort of C1, C2 thing where you have an equation, you plug back in your y and x values to work out the constant. But the difference is now you haven't got one constant, you've got two, so you have to differentiate and use a second equation and then solve it simultaneously. We're getting very used to simultaneous equations at this point, I'm sure. This is not very hard for us. So the difficult bit is to remember to differentiate and plugging them into both equations. That's it. Have a go. Get stuck in with some different equations and see if you can work out what the what the actual specific solutions to these equations are given their boundary conditions. Good luck.